Don Patterson said I'm the anchor of this session, which is hard to believe. I think he meant it in a nice way, but I always think of an anchor as something that drags something else down to the bottom. So I'm not sure that he didn't mean it that way too. What I'm going to talk to you about today is something very basic, and that's maintenance of a GC column, specifically trimming it to restore the performance after you have non-volatile material collect on the front of the column and sabotage its performance. And one of the things that inspired me to do this was we get a lot of tech service calls for this type of thing. Not only that, but last year at the Thermopop Symposium, I saw a talk by Heidi Fiedler and later one by Bert von Bavel, where they're actually looking at analyzing POPs or sponsoring programs where POPs are analyzed in developing countries. And a lot of these people are still using gas chromatography with electron capture detector, not necessarily high-res MS, etc. They don't have a lot of money to spend on the analysis itself, so anything they can do to extend the lifetime of their system, including something like a GC column, which is quite expensive in some of these countries, is going to be well received. Let's see if I can find the laser pointer here. The first thing I want to do, though, is start with something like determining the GC column length and tell you why it's important. Some of you, I'm sure, already know right now that for most modern GC softwares, you have to enter the length of the column into the system to actually control the carrier gas flow accurately. The other reason that determining a GC column length can be important is that when you're getting ready to translate a method, and I'm going to talk about that today, after column trimming, you need to put an accurate column length in there also. This is just an example of a screen capture of some of the software that I use that actually shows you where you put the column length in. And I've entered a 30-meter column length, 250 micron or 0.25 millimeter ID, etc. here, so that the flow control can be accurate. Now, how many people believe that when you buy a 30-meter column that's actually 30 meters in length? Do you think it's 25 meters? No, it's not like that. But it used to be that sometimes you'd find them as long as 35 meters, and this has a significant effect on what the flow is going to be and what the linear velocity is going to be if your column is actually a different length than you think it is and you're putting it into a system like this. So I've entered 30 meters nominal, but I'll show you that it's not always the case. Now there are several ways that you can calculate the length of a GC column, and I've put just a simple mathematic way up here. Now I use the word simple, but it's not as simple as it seems. Column length is equal to the circumference times the number of turns or loops of the GC column. The circumference is equal to pi times the diameter, and if you can determine the diameter of the column on the cage, which is really simple by measuring it or knowing that we use like a 7-inch cage, you can then count the turns of the column, not the simple part, and figure out what the column length is. Now here's an example for one of our columns, and again it's based on the fact that the cage is a certain diameter. It's about 0.175 meters, 17.5 centimeters. And if you go through the math, you eventually end up, after counting the turns, that we have a 30.8 meter column in this example. So it's not exactly 30 meters, and that slight difference will cause a little bit difference in the flow. In this case, not much. One thing I should mention is that what you don't want to do when you're trying to determine the length of the column is actually uncoil it from the cage, lay it out in the lab, measure it, and then try to put it back on the cage. That's not recommended at all. You haven't ever done that, have you, Don? I didn't think so. Okay, simple example. Again, get out your trusty plastic measuring device, measure the diameter. You can actually count the loops. This is not fun when you're an old man like me. You can't see these loops. You're going to get it wrong several times, so accuracy is not going to be that great. Some people like to use something like a wooden dowel or a toothpick or whatever. Maybe it's best to count these loops after lunch. But that's one way you can actually determine the length of a GC column. And quite frankly, that's the way a lot of people used to do it at Restek when they were looking to get the column length very accurately for some study work that we used to do. But there's another way that's much more simple, and that's to use one of these column pressure flow calculators that you can download off the web. And I'll show you how to do that. This is what the thing looks like as it's presented when you fire it up. But you can actually install your GC column, establish the head pressure. You can split inject a non-retained substance, like and I propose a few right here that are routinely used, like methane for a flame ionization detector. You can use something like methylene chloride for an electron capture detector, or air for a mass spectrometer and monitor 28 mass to charge, and you'll be able to calculate the holdup time or the dead volume. You can then use this column calculator, pressure flow calculator, to match the column length with the measured holdup time. And I'll run you through an example to show you how that's done. Okay, so there's a peak. Now I have to give a nod to the Grateful Dead since we're in San Francisco, so dead volume is synonymous with holdup time. And that's what we're going to measure right here. And here's an example of how we can do a dead volume determination with an electron capture detector. We install the column, we enter it into the GC software, we establish a desired flow or linear velocity through a head pressure essentially. We want to have the oven temperature up to 200 degrees C because we're actually going to inject a solvent that's slightly retained in this case. We don't want it at an ambient temperature. We can note the retention time in seconds at the peak apex right here. And then if we look at what the average linear velocity is in centimeters per second, it's around 48 centimeters per second. But again, this is all based on us assuming the column vendor or the friend that used the column before you actually had it tagged at 30 meters, and that's usually not the case. Okay, so let's look at the column flow calculator right here. Here we can see the length, 30 meters, 0.25 millimeters ID. We've got it at 200. And theoretically, under these conditions, our holdup time should be 63 seconds or 1.05 minutes. But we've got a couple of guys working in the lab, my colleagues Scott Grossman and Eberhard Kuhn, who have used the methylene chloride technique to actually find out that their holdup time is 65.4 seconds. Now, what's going on there? Well, some people would say it's just the slow pace of life in central Pennsylvania, but I think it's something else. So what we want to do to actually find out what the column length is, because in this case it appears it's a bit longer since it's taking longer to elute through the column, is actually adjust the holdup time value by increasing, in this case, or decreasing the column length. So you see I've gone from 30 to 30.3, and now the holdup time is actually changing here. And what we can do is click on that button until we get to 65.4 seconds, right? Which is what Scott and Eberhard determined, assuming they were sober at the time. And you can see now we have a 30.6 meter column length. And this way we can actually enter that into our software properly and make sure that our EPC, or electronic pneumatic control, is actually functioning and giving us the flow that we desire. Now, there's a couple of important reasons for this. One is we're trying to get reproducibility on methods. Another good reason was mentioned today, and that is you typically want to have the same source pressure in a mass spectrometer every time. And if you have the same outlet flow, that'll be a good thing in the long run. The work I'm going to show you that I did today involving the column trimming, now that we know how to actually set an accurate column length, which is going to be important for trimming and method translation to get the same separation, or essentially the same separation, is our RTXCO pesticides column. This is a selective column that we use for organochlorine pesticide work, a la EPA method 8081B, which includes a variety of pesticides. Typically we monitor about 20 and a couple of surrogates, tetrachloroemxylene and decachlorobiphenyl. Okay, now we can actually take this 30.6 meters column It's just like Restek to always give you a little bit extra here, and actually employ a 20.7 degrees C per minute program rate and effect a nice separation of these organochlorine pesticides via GCECD in about 13 minutes. And if you look relatively closely and you had the time to count them, you'd see there's 22 there, and that they're all almost separated at least to baseline. But what happens? We actually run some samples and they're dirty often. So we need to actually trim our GC column to restore its performance, because non-volatile material, dirt if you will, builds up on the head of the column and starts causing problems with the chromatography. And so that's what we're going to work our way through for the rest of the presentation, is how to properly trim a GC column. It's not just as simple as cutting it and putting it back in and going again, especially when you're looking at a selective column like the CL pesticides that tends to move peaks around depending on the elution temperature for the component of interest. Let's take a look and see what happens. Briefly, let's turn right and look at a pH separation where we actually have tailing peaks right here. We were making some injections of some polymeric material, and you can see it corrupted the liner in the front of the GC column, and we have these horrible peak tails. And if we look closely at something like fluoranthene and pyrene, you can see this is not optimum. This is definitely not what we want to see. Well, by simply changing the bottom seal for the inlet and trimming the GC column slightly, we have a nicely restored performance and perfectly symmetrical peaks for fluoranthene and pyrene. That's what we're talking about when we're talking about restoring column performance with trimming as our maintenance activity. Okay, back to the 30.6 meter, 20.7 degrees C per minute, organochlorine pesticides. Here's how we trim and method translate. Again, this is a handy dandy program you can download from the web, and essentially what it allows you to do is to actually enter a starting program, which is the one that we just ran our initial chromatogram of. If we trim, in this case we took about a meter off, you can actually enter this into the translator. The flow is going to remain the same, and essentially what you get is a new GC oven program where the rate is 21.6 degrees C per minute when it was previously 20.7. Now, why do we do this? We do this because we want things to elute at the same temperature. And if you look at this 29.7 meter chromatogram with the increased program rate, the only thing you really see that's extremely noticeable is that the time shrinks down a little bit for the decachlorobiphenyl elution. Other than that, the chromatogram pretty much looks the same, and I'll prove that to you for some more critical separations later on. But what I want to do right now is just continue to trim the column and go from 29.7 to 28.6. We adjusted the program rate with the method translator. Time is shrinking a little bit to 26.6. Now we've got 4 meters off of this column, which is a lot of maintenance. There's a lot of days of maintenance in there. And the chromatogram essentially looks the same. We're down to 21.8 meters now, a heck of a lot of trimming done on the column. And for all practical purposes, the chromatogram pretty much still looks the same. It's only when we get down to 15.7 meters, or about half of the original column length, that we start to see a degradation in the separation right here between DDE and endosulfan 1. So this is, I think, relatively surprising to people that they can maintain such good separations when they're heavily trimming their column. Now, I mentioned that I was going to zoom in on some of the details. These are the important compounds right here, DDE and endosulfan 1, the ones that tend to elute closest together. And you can see as we go from 30.6 meters, 29.7 meters, 28.6 meters, we're actually doing a pretty good job of maintaining the separation for not only those components, but for all the others in that particular chromatogram. We do the same for 26.6 and 21.8. Again, it's only when we get down to about half the column that we start to struggle. And I sometimes wonder if it's not because we just can't keep up in program rate. We're really going fast at this point, and even with a 240 volt system, it's a bit of a challenge to actually program at 50 degrees C per minute for most gas chromatographs. So it may be just as likely that we're not able to program as fast here as we're actually losing plates on this column to sabotage this particular separation. Now, one thing you may wonder is, what does this do other than the fact that it reduces the analysis time? The other thing it does, not surprisingly, is that your peaks get narrower. Now, some people might figure that's a good thing. Some people might figure it's a bad thing. It's not a challenge with an electron capture detector for acquisition rate, but if you actually have a slower acquiring mass spectrometer, it might be a bit of a bad point that your peaks are actually getting narrower as you trim the column. Now, a lot of people might say, well, there's one other bad thing that can happen, and that is your retention times are changing, and now you're going to have to move your selected ion monitoring or your selected reaction monitoring windows around. And I just wanted to show you how simple it is to relate the retention time changes to actually column length changes. And if you just consider, these are the original retention times, and these are the ratios of the retention times for the 29.7 meter to the original retention times off the 30.6 ratio right here. Here's the column length ratio. So it'd be pretty simple to actually move your selected ion monitoring windows or your selected reaction monitoring windows, I think, based on column length. They're coming out pretty good right here if you look at it. It's only when we get to here we slip a little bit, but still not too bad, I think. Okay, now there's a couple other things that can occur. How much time do I have left? I need to... Almost done. We're going to be almost done very soon. Okay, so there's a couple other things that we find happening when tech service people call in, and that is people trim their columns, but they don't update anything. They don't update the oven programming. They don't update the length. And here, right here, what you see is a 21.8 meter column where we didn't change anything in the software, and now we have a coelution. And I already showed you earlier that if you do this properly, you don't have that coelution. And the reason you have it here is because you actually have an elution temperature difference. You see the elution temperature here and here? For a selective column, that's very important. You need to maintain the separation. You're going to have to actually update the column length and the program rate to maintain the separation. If we do it the other way around, where we actually update 21.8 meters, but we don't change the oven program rate, we don't method translate, we've got the same problem, a coelution. So that's what gets a lot of people hung up. They'll trim their column, but they won't update things properly, and that doesn't allow them to maintain the lifetime of the column very well. So accurate column length is important for accurate carrier glass flow by electronic pneumatic control. But the other thing you have to do is make sure you translate the method. After you start trimming your column, translate the method, and you'll be able to preserve the separation for a lot longer than you might think. My colleague Michelle Misselwitz did a poster at the BFR workshop just this week, and this works very well for BDEs. This is an interesting example because we went from about a 15 meter column right here to a 8 meter column, trimmed a lot off the column. We're still able to do very good on 49 and 71. We often get asked why we don't make a longer column for BDE analysis to account for some maintenance activities, and this is why, because if you properly translate it, you don't really need it. So let's finish up before Hans kicks me off the stage here and say that determining GC column length is important. Performing method translation is just as important and hopefully important to you to save a few monies and to keep uptime a little bit. You can realize that your GC columns will separate, i.e. last a lot longer even after column trimming. And with that, I'll thank you for your attention.